Hi there, I'm an old guy and I do maths. Now, if you've been in the business of looking at quadratics at school or at university or just out of interest, if that's possible, you may well have come across the quadratic formula. And if you haven't, have a look at my video on that, and this will become probably a little more understandable. But part of the quadratic formula is this little bit of algebra here, b squared minus 4ac. And this is called the discriminant. And when you apply this, you can discover whether your quadratic equation has no solutions or no real solutions, one solution or two solutions. Now, what does that mean? It means solutions for x, which means does this quadratic, when graphed, hit the x-axis in two places, one place, or not at all? Okay, so what are the circumstances in which this happens? Right, let's take a look at example A here. X squared plus 5x plus 6, which you will probably recognize as one of my favorite quadratics because it's nice and simple. When we apply this, b squared minus 4 times a times c, what we discover is that b squared, 5, minus 4 times a, 1, times c, 6, is greater than 0. Now what that means is that this thing has two solutions for x. And when we work out those solutions, or when we factorize this, and then work out the solutions, when we factorize it, we find that we get two brackets, x plus 3, x plus 2. The factors of 6 are 3 and 2. 3 and 2 add to 5. There's another factor, 6 and 1, but 6 plus 1 does not add to 5. So these are the factors. Using null factor law, which you might be familiar with, and if you're not, have a look at my video on that. It's very simple, it's very fast and easy. X is equal to negative 3 or negative 2, so we have two solutions. And what this means is that when you graph this thing on a Cartesian plane that hopefully doesn't look as ropey as mine, you get two x-intercepts, negative 3 and negative 2, and the y-intercept, which you see here, 6. Okay, so that's the first example. Now, what's coming up is an example of what's known as a perfect square. X squared plus 10x plus 25. When you factorize this, what you do is you look for the factors of 25 that add to 10. Surprise, surprise, there are only two factors of 25 that add to 10, 5 and 5. So you can write this equation like this if you want. It is, in fact, if you properly factorize this, I suppose, I don't know, you can write it like that, but the instruction here is to multiply that by that. They are the same, so you can write it like that. It is a perfect square. And what we're going to do is we're going to apply this discriminant formula to this. So b squared, 10 squared, 4 times a is 1, c is 25, so we get 10 squared minus 4 times 1 times 25, and what we discover is that that equals 0. Why? Because that is 100, 4 times 25 is 100, and we're subtracting, we get 0. What that means is that this thing has one real solution. What does that mean? It means that it hits the x-axis once. It touches the x-axis in one position, and that is negative 5. Why is it negative 5? Because what we have to do to find the solution, given these factors, is we apply null factor law, and we discover that x is equal to negative 5. It is that point there. C is this point here, 25, the y-intercept. Okay, so what have we seen so far? We've seen two solutions, one solution. Now we're going to have a look at no solutions. Well, what's sometimes lazily called no solutions, or no solution, but actually, technically speaking, is no real solution. And what that means is that there's a solution in, shall we say, complex numbers or something like that. But for all practical purposes, there's no real solution to the equation that you're looking at. So what we do is we try factorizing this. We get nowhere. We pop it into this little formula here, the discriminant. So 5 squared, b squared, minus 4 times 1 times 9, that number there. And what we discover is that this is less than 0 when we work it out. It's 25 minus 36. So that tells us that we have no real solutions. It doesn't mean you can't graph this thing. All it means is that it does not hit the x-axis. We have the y-intercept here, which we get from that. And this thing does have a turning point, which we can figure out. And I'll show you what I've done about that down below. Okay, so here we are. So what I did to get the turning point is I did the first 3 or 4 steps of completing the square. Just let me get the rest of that into frame. And if this is a complete mystery, give up now and go and have a look at the video on completing the square and come back to this and it will make sense, I promise you. Anyway, we go through the first 3 steps of completing the square. So what we do is we create in this space here a perfect square by halving this number and squaring it. And because we did that, we have to take the same number away. So we haven't effectively changed this equation. And I'm just going to go through this really quickly because I don't want this to turn into a tutorial on completing the square. This is simply how I found the turning point form for this thing. It's not the only way in which I could do it. If I'd worked out what the x value of this point is, I could simply have put it into the equation. But you can convert this to turning point form, and that is what I've done here. So we can simplify this. We can write it as x plus 5 over 2 all squared, and then we just have to work out this number here. And in working out this number here, we write 9 as a fraction over 4, 36 over 4, and we already have 25 over 4, so we subtract 25 over 4 from 36 over 4, and the answer that we get is 11 over 4. This is the turning point form for the equation that you saw here. And the negative of this, using null factor law, is the x value of the turning point coordinate. So it's negative 5 over 2 or negative 2.5. This, without any adjustment, is the y coordinate, and that can be written as 2.75, or both of these can be left as fractions. Now, that was a bit of a workout. I hope it was useful. It may take a little bit of getting used to, so feel free to go back through the video. I hope I didn't go through it too fast. Anyway, there's a thing on YouTube which allows you to slow it down, so I guess I don't know, does my voice go even deeper? We'll see. Thanks very much for watching, however. See you next time. Bye.